I'm going to get started with fluids today, beginning with 8.1, density and pressure. So first of all, a fluid is anything that can flow. So this means a liquid or a gas. And at first we'll look at fluids at rest, which is called fluid statics. Okay, so we've seen this equation for density before, but just to review, the density of a substance is equal to its mass divided by its volume. So our equation looks like this with the symbol for density being rho, and the SI unit is kilograms per meter cubed. Then we have the mass in kilograms over the volume in meters cubed. And these are all the SI units, but another common unit for density is grams per centimeter cubed. So I want to show you quickly, just to review, how we convert between the two. So the density of water is 1 gram per centimeter cubed. Let's convert that into kilograms per meter cubed. Okay, so I'm going to multiply by 1 kilogram over 10 to the 3 grams to cancel the grams. And then we'll do the centimeters cubed, so 1 centimeter in the numerator over 10 to the negative 2 meters. And then we'll need to cube that whole factor. And then we can multiply through. So we have 1 times 10 to the negative 3 when we move that up, times 10 to the positive 6 when we have negative 6 in the denominator and move it up to positive 6 in the numerator. So this is going to be 1 times 10 to the 3, or 1,000 kilograms per meter cubed. And you can remember this kind of as a shortcut because any number here we would end up with the same conversion. So if you're starting in grams per centimeter cubed, you can multiply by 1,000 to convert to kilograms per meter cubed. And in general, this is a useful reference to remember the density of water. So I'll just write 2 notes for density here. One is that the density of water is 1,000 kilograms per meter cubed, or 1 gram per centimeter cubed. And we know now after our section on thermal expansion that this is actually at 4 degrees. So at 4 degrees Celsius, this is the density of water, but it doesn't vary much from that, and certainly not to 1 or 2 sig figs around normal room temperatures. So you can use this and remember this if the question is asking you about water. We can always use that density. The second point notes about density is that the density of a substance depends on its thermodynamic conditions. So temperature and pressure mainly. So for example, if we were to increase the temperature of a substance, those molecules would start to move around and spread out, and this would increase the volume, which would decrease the density. And we could say something similar for pressure. If we were to increase the pressure of a substance, that would compact the substance and decrease the volume, which would then increase the density. So when we use a constant density for a substance, that actually depends on those thermodynamic conditions. All right, let's try the first example on density. Okay, so we have a spherical ball of iron with a radius of 2.5 centimeters, has a mass of 510 grams. Calculate the density of iron. If you had a wooden cube of density 0.5 grams per centimeter cubed, how large would it have to be to have the same mass as the iron sphere? Okay, so in the first part, we can use the radius and the mass of the iron to calculate its density. So here I've written the density of iron equals mass over volume, and then I'm going to plug in the expression for the volume of a sphere, which is 4 over 3 pi r cubed. Okay, so plugging that in, I have the mass, 510 grams. We can do this in grams per centimeter cubed, over 4 over 3 pi, 2.5 centimeters cubed. And that gives me a density of 7.792 grams per centimeter cubed. And you could just multiply by 1,000 to convert into the SI units, which would be 7,792 kilograms per meter cubed. All right, so in B, we have a cube now, so all side lengths are the same, length L we can call that, and we need to find the volume of that cube if it has the same mass as this iron sphere. All right, so the volume of the cube will be mass over density, just rearranging this formula for density, and then the length, so volume is length times width times height, and they're all equivalent this time, so length cubed. All right, so length cubed is mass over the density of wood, and then we need to take the cube root of that in order to solve for the length. So the mass is 510 grams over 0.5 grams per centimeter cubed for the wood, which gives me 10.1 centimeters for the length of that side. The next concept that I want to introduce is pressure. So let's consider a force that acts over a region of area A. Something like this, where the area of this surface would be A, and the force is applied at all regions over that area. Then the pressure is defined as the force per unit area exerted over that region. It looks like this, so pressure has units of newtons per meter squared equals force in newtons over area in meters squared. So the unit for pressure is newtons per meter squared, which is an SI derived unit that has a name. It's called a Pascal. So 1 Pascal, PA, equals 1 Newton per meter squared. So we can see that as the force is applied over a smaller area, the pressure would increase. So let's look at the first example on pressure. A person of mass 60 kilograms stands on the floor. What is the pressure exerted by the person on the floor if, part A, the person stands on 2 feet, which is an area of 500 centimeters squared, B, 1 foot, 250 centimeters squared, or C, 1 toe, 10 centimeters squared? Okay, so in each case, the force is going to be the same because it's equal to the weight of the person. So we can calculate that using Fg equals mg, 60 kilograms times 9.8 newtons per kilogram, which is 588 newtons. Then if you notice our area is in centimeters squared, we will need to convert everything into SI units in order to have our pressure in pascals. Okay, so I've done one conversion here, the rest will be the same essentially, so we multiply by 10 to the negative 2 meters per centimeter, and squaring that factor gives me 0.05 meters squared. Okay, so now we can plug into our equation for pressure, force per unit area. So when this person is standing on 2 feet, that's dividing by 0.05 meters squared, which is 11,760 pascals when you divide that. Okay, now in part B, we can see the person is standing on only half that area. So looking at the relationship, pressure is inversely proportional to area. So we should find that if we cut this area in half, the pressure doubles. So it increases by the same factor. But let's check using the same relationship. So we'll have force over area, 588 newtons, divided by 0.025 meters squared. And we get 23,520 pascals, which is double this value here, so that did work as expected. And then the last case, it's the person's standing on 1 toe, so 588 newtons over 0.01 meters squared. Oh, 0.001, there we go, which gives me a pressure of 588,000 pascals, or 588 kilopascals. So as we expected, with the force being constant, applying that over a smaller area means a higher force density per unit area, or a higher pressure. Okay, so I just have some notes to say about looking at pressure in gases. Okay, so in a gas, we can imagine that the pressure results from gas molecules moving around, colliding, and this net effect of collisions creates a force which applied over an area is a pressure. And it's a similar thing for liquids. So the liquids will move around, vibrate, collide, and create pressure within the liquid. So fluids in general exert pressure forces on surfaces in contact with the fluid. So if it's in a container, on the walls of the container. And also on other regions of the fluid. So all of these fluid molecules, in a sense, exert pressure on each other, creating pressure within the fluid. And as an example, we know this happens in the liquid. If you were to poke a hole, maybe in a can of a drink near the bottom, you would see that that liquid pushes out of that hole. And that's because there is pressure inside of that can, and then it's forcing the liquid out of the hole of that container. We'll mostly study liquids because they are incompressible, which means that their density depends very little on pressure, so we can take that density to be constant. Though everything we look at will apply to any fluids where the density is constant. Okay, so we also want to describe how pressure varies with depth. And if you can just consider two examples that show us that pressure increases with depth in a fluid. So the first one, we can think about diving underwater or scuba diving. If you were to do this, then we would find that as you dive to a greater depth, the pressure would increase. So we know that's true. Another one is if you were to maybe poke holes in a container, similar to what I was talking about before. Picture some kind of container like this of liquid. And then if we poke holes here, we know liquid will come out all of these areas, but it will come out the fastest with the greatest speed at the lowest depth. So that's telling us that the pressure is higher closer to the bottom of that container or at the greater depth. So logically, we know that pressure increases with depth. Okay, so let's consider a fluid. Say a liquid. Consider a region of liquid in a container, like this. So there's nothing in there, no object, but I'm just interested in that region within the liquid. Okay, so if we look at the forces on that area of liquid, I've drawn it as a cube, but the specific shape isn't important. If we look at the forces for the free body diagram, of course we have gravity acting on that region within the fluid. We also have pressure exerting forces on all sides of that region. So we would have pressure from the bottom, the sides, and the top. So when we write a force from pressure, we can write it using the definition of pressure. So if pressure is force per unit area, force is pressure times area. Okay, so on this it would be the pressure from the sides times the area. On this side as well, the pressure of the sides times the area. Here we have the pressure at the bottom times the area. And I'll use P naught here to represent the pressure at the top. So P naught is the pressure at the top of the fluid region. Now, the pressure on the sides here will cancel out. They're going to be equal and in opposite directions. We know they're going to be equal because the area of the shape has the same area on both sides. As well on the top, I'm looking at a shape with a uniform area on all sides. And also because it varies with depth, and these sides are at the same depth all along the sides. So though the depth would vary, it would vary in the same way on this side, and we would have equal and opposite forces all over the side, which would create the same pressure. All right, so those are equal and opposite, and they cancel out. Let's just get rid of them. And so we're left with these forces here. Okay, so then let's look at a proper free body diagram for this region of fluid and write out the net force acting on it. So from the bottom surface, we have an upward force, which is pressure times area. Then acting down, we have the weight and the force from the top of the region, which is pushing down, and that's P naught A. we know that the pressure on the bottom is going to be higher than the pressure on the top because pressure increases with depth. So we do know that this force will actually be greater than this pressure force that's acting down. Okay, so PA minus P naught A, just summing these and equaling to 0, minus the weight equals 0. Now I can divide everything by A and rearrange for the pressure at a depth. Here the depth will be the height of that region, so we're going to call the depth H. Okay, so you want to think about it like this. This is H, the height of that fluid region. So often in this section, what we'll do is plug in for the mass and write it in terms of density and volume, because it's likely that we have the density of the fluid that's in question. Okay, so the mass will be the density of the fluid, I'll put subscript F for fluid, times the volume, which is the density of the fluid times the area times the height. If I plug that in here, we see that area cancels, and I end up with the pressure at height H equals P naught, the pressure at the top of the region, plus rho, the density of the fluid, G, and then H, which is the depth in this case, or the total height of that fluid region or object. Okay, so all of the pressures here are in pascals, which means we need density in kilograms per meter cubed. G is 9.8 meters per second squared, and then the depth will be in meters. So I'll just erase this to note that the pressure that we're writing here is called absolute pressure. And this initial pressure at the top of the region, if that surface is open to the environment, then that will be atmospheric pressure. So if open to the atmosphere, there we go, we have P naught equals PA, which is 1.013 times 10 to the 5 pascals. This is the pressure that we experience every day on the surface of Earth due to the weight of the atmosphere above us. And so that is a standard value that everything we're subject to here near the surface of Earth at sea level has atmospheric pressure. So often a quantity that's used instead is gauge pressure, which gives the difference between the atmospheric pressure and the absolute pressure. So to calculate gauge pressure will be Pg equals the absolute pressure minus atmospheric pressure. So it gives the difference, and this is often useful since everything we experience is generally subject to atmospheric pressure. So it can give a better way to compare different pressures of different substances. But okay, let's look at some notes on pressure in fluids. Okay, so my first note is that the pressure must be equal along a horizontal line. So this rule is for fluids at hydrostatic equilibrium that are connected and of one type. So in this case, we have to have if we draw a horizontal line anywhere in the fluid, the pressure will be the same along that point. And this follows from the fact that pressure depends on depth and increases with depth. And also if there was a pressure gradient, if it varied along that height, we would see that the liquid would move until it comes to an equilibrium point where the pressure is constant everywhere along that line. So what follows from this is my second point here, that a connected liquid of one type in equilibrium rises to the same height in all open regions of the container. So we know that if it's open, the pressure at the top has to be atmospheric pressure. Then, because of this horizontal line rule, at the bottom, the pressure all the way along the bottom must be equal as well. So if I write that out, I have P equals P naught plus rho GH. And if P minus P naught has to be the same everywhere, we can see that the height has to be the same everywhere as well for all open regions of that container. And my last point is that, as we know now, pressure does increase with depth, but why is because the pressure at any point is due to the weight of the fluid above that point. So as we go to lower depth, there's more fluid that has to be supported in a sense above that point. So the force of that weight pushing down creates a higher pressure at any point. Okay, so I have two examples to do for pressure. Let's look at the first one. The surface of a water tank that is open to the atmosphere is 30 meters above a water faucet in the kitchen of a house. Part A, calculate the absolute pressure at the faucet, and then B is calculate the gauge pressure at the faucet. Okay, so I've drawn a sketch. It looks something like this, where the top of the water tank is open to the atmosphere. So the pressure at the top would be equal to atmospheric pressure. 30 meters below that, we're looking at the absolute pressure, pressure P. Okay, so we can just apply the equation for pressure at a depth to this case. So P equals P naught plus rho F GH. So we have atmospheric pressure plus 1,000 kilograms per meter cubed for the density of water, 9.8 meters per second squared for G times 30 meters. And that gives me 3.95 times 10 to the 5 pascals. Okay, now the gauge pressure is the difference between absolute pressure and atmospheric pressure. So we take that pressure we just found and subtract atmospheric and get this value. However, if you're in this case where the initial pressure at the top of the region is open to the atmosphere, we can notice that if we subtract these two, we get gauge pressure as well. So you could have also used this part of the equation to calculate the gauge pressure when P naught equals PA. And you can try that, you should get the same result there. Okay, one more example. Okay, so the pressure at the surface of the Earth is on average 1.013 times 10 to the 5 pascals. The radius of the Earth is approximately 6.38 times 10 to the 6 meters. Calculate the mass of the atmosphere. Okay, so this is based on the idea or the principle that the pressure at any point is due to the weight of the mass above that point. So on Earth, when we feel this pressure, this is due to the weight of the atmosphere. And the weight of that atmosphere is exerted all around the surface of the planet, which we can take to be a sphere in this case. So the pressure is due to the weight over the area, which is mg over the area. We can rearrange to solve for the mass. So I have the mass equals the pressure times the area over g. And then the surface area of the sphere is 4 pi r squared. So plugging that in here, and then our numbers here, we have atmospheric pressure, 1.013 times 10 to the 5 pascals, times 4 pi, the radius squared, 6.38 times 10 to the 6 meters squared, divided by g, which gives me 5.29 times 10 to the 18 kilograms. Okay, that's all for this section. Next, we'll look at solving hydrostatic problems.